Hello students, we have completed the area of forces, but today class we are going to look at something very important in the story of physics, which is the principle of conservation of linear momentum. I'm going to be very more brief in how to be solving problems, or how we have the derivation of this particular equation we use to be solving problems under this area. That's going to be the area of focus I'm going to be stressing on. First of all, we look at what's called principle of linear momentum. If you have not looked into the first previous slide that I have, when we are talking about what momentum here, I'll just bring an instance, or I'll just bring a recap of what we have done in regards to this momentum. First of all, when we say momentum simply means mass times velocity. This is what we call momentum. That means the mass here times the velocity. That gives us what we call momentum, the product of mass and velocity. Then from this part, we are going to look at the principle of conservation of linear momentum. But before we look at the principle, there is something very important we need to note in regards to this. That means we need to know what is collision. Collision, first of all, simply means in the study of physics, don't say collision. It simply means when we have two bodies that come in contact forcefully, it's either they go the same velocity or different velocity, is what we call collision, right? But maybe whilst we are going to be looking at this this particular area proper. But before we look at this, our focus is going to be this particular principle. And the principle states that the provided no external force acts on the system of collision. That means when the two bodies come in contact, provided no external force acts on it, the total energy there or linear momentum there is going to of the bodies there or system is going to remain constant. That means the energy or the momentum that the bodies are going to have before collision, then after collision is going to be equal to the momentum or linear momentum that they are going to have after collision. That's what this particular principle is saying. That means we are going to conserve, right, momentum in this case. Now let's just see what we have here in this case. I'm going to represent two things here, or some diagrams here, to explain this particular principle much more better using the laws of motion. Now the first is, let's just say we have two bodies together. I have here body A, I have body B, I have body A, or let's just say I have body B here, I have body A, I have body B, body A, I have body B. Now these are three bodies. Now for this one we are saying before, let's just say before collision. For the first one here is before collision. Now the next one here, let's say this one is during collision. Right? This one is during collision and this one is after collision. These are the three instances we have. Now let's just say before collision, this body is bringing a velocity and this also is bringing a velocity. Right? They are bringing different velocities. These particular two bodies, they come here and they collide together. If these bodies collide together, let's just say they collide here. If they collide together, that means this one is bringing a velocity, this also is bringing a velocity. When they come here, they collide together. When they collide together, then here is after collision. It's either they go this way or they go this way. It depends on the velocity that they are bringing. That means collision here, if two bodies come in contact, like two cars come in contact, it does not depend that says, it does not going to determine that the mass, maybe sometimes the bigger one is going to move this one, or maybe the smaller is going, they are going in the direction of the smaller one. That means they don't just have bigger object and smaller object. It does not necessarily mean that this particular bigger object will take the velocity of this one here. It does not mean. That means we will take the direction of the smaller one. It does not mean. What determines here is the velocity that each of these one they are bringing. If they are bringing a greater velocity, that means if this one is bringing a greater velocity, that means this particular is they are going to move in this part. If this one is bringing a greater velocity, also they are going to move into this part. So if the mass of that particular object cannot just determine, right, the movement, it depends on the velocity that they are bringing. Now from these instances we have here on the board, let us see if we can able to analyze this particular linear momentum. Now for linear momentum, I've explained that provided there is no external force act on the system of collision, we are saying the energy remain constant, right? The energy remain constant. Now let's just say we have this one here. These are two bodies. They are bringing two velocities together. Now in this case, let's come here. This one here, I'm going to they collide here. Right? This is during collision. And during collision, I'm going to take from Newton's third law, right? Newton's third law. Newton's third law says what? For any action, right, there is an opposite reaction. That's what the third law says. For any action, there is an opposite reaction. If that be the case, if I express into mathematics, that means F here equal to minus F here. That means F represents the force, that means the action, equal to this one represents opposite, this minus F represents opposite what? Reaction. That's what the third law says. If you have following our classes, I think we have made something in regards to this. So this is what we have from this point. Then secondly, this one now we are saying from A here, that means before collision, now the bodies collide together here. When they collide, if I'm to express it into mathematics, from the third law, I'm saying for this collision, that means the principle of linear momentum here, from this point I will say F is equal to minus F. So this is what I have. So now in this case, if I have F equal to minus F from Newton's second law, because they are going to collide. Now let me just say this. Whenever, for the third law, whenever anybody so far, any object, if it exerts a force on that object, just have it in mind that that force, that object also is also giving you opposite force, right? It's also giving you opposite action or reaction, right? So this is what we are saying here. So if these two bodies collide here, if body A here is giving force to this also is giving force to this. That means opposite force. That's why we have F equal to minus F from this point. Now I have F here and I have F here. Now from the second law, I will take it from the second law of Newton's law of motion. Right? The second law says F is equal to what? ma. That means the time rate of change of momentum is directly proportional to the force applied. In that regard, I have F equal to what? Ma. So from this F equal to ma, express this one now. I will express this one now. Now in this figures, I'm having mass A, I have acceleration A here, I have mass B, I have acceleration B here. Now in this regards, I will decide to bring the value of this A, that means acceleration. Now from acceleration, under the basis of motion, linear motion, we say acceleration simply means the time rate of a change of velocity. And when we say time rate, we are referring to, when we use word rate in physics or in science, we are referring to time. If I use word time rate, right, of velocity, that means I'm talking about velocity all over time. So acceleration by definition we are saying is the rate of what? Change of velocity. That means in that regards, I will have A, mathematical is going to be A change in what? Velocity all over time, because I'm using the word time rate or rate of something there. So this is what I have. If I express it into mathematics, I will have A equal to V minus U here all over T. So the value of this particular A is this. So I will substitute this value into this equation, right? That means now I will have MA here, because I'm having A here, into the value of this one there is what? V minus U all over T. This is what I have. All equal to, I will still have what? A minus here. For this, I will have minus M into, I have V minus U all over T, bracket close. This is what I have. So in that regard, the next thing I'm going to do now is, now I will decide to, this one is B, this one is B because it's after collision. Now I will decide to like expand the bracket. Before I expand the bracket, there is something you need to note in regards to this. Now I'm seeing the denominators are the same, right? If denominators are the same and I'm having a minus sign here, I will not like see in mathematics, maybe sometimes if I have something like this, I have plus, something like this, I will find what we call the LCM, right? But now in this case, I will not decide to find LCM because this time and this time they are the same. The time before collision is the same as the time after collision, so they have the same value. I will decide to cancel them out. I will subtract from each of these. That means t time minus this one here is not the same thing. Or I will decide to cancel it, right? It is mathematically correct. So because they have the same value. So if this one cancel this, what remains now is going to be a here. That means into v minus u bracket close all equal to minus this part here into v minus u bracket close. So this is what I have. The next step is I will decide to expand the bracket. If I'm going to expand the bracket, this time means I'm going to have ma here. That means I'm going to have va. Then I have a minus sign. Then this time means I will still have mu. I have a, all equal to this time means I will have mb here. Then I have vb. Then I have minus, right? This times u here is b here, u b here. So this is what I have. From this point, let's just see from this point what we have from this point. From this point, I'm having this, right? I'm having this here. Now this one is linear, right? This one is an equation, but it is linear. It is just something straight. In that regard, if I have this, I will decide to like create the like terms or transpose, do the same thing, right? But now in this case, if I expand, because there is a minus here, let me go over this. There is a minus here. This time this gives me a minus, right? I'll have minus mb here, vb here for this part. Then minus here is plus. I'm going to have plus here. Then if I multiply this time, I'll have b here, ub here, right? So this is what I have. After having this, I will collect like terms. If I'm to collect like terms, I'm seeing ma here, va here. I'm also seeing mb here. Because I'm going to collect what we call the v is what is common here. So because m is all over, so I will decide to take v in one place and u in one place because m is common in both of these particular entities. So now in this regard, I will take this mv then mv here in one place. So I will take this mv. That means I have mv here. Now this one is a and this also is a. Then I'm still having mb minus mb here. So this I will take this one here and transpose it over, become what? Plus. That means I have plus m sub b here, then I have v sub b. All equal to, now I'm seeing something here, I'm seeing this man here. This man is mu and this also is bu. So in that regards, I will decide to like take this over and cross it over, right? I will take this and cross it over. So in that regards, I will still have something like, if this one goes over, it becomes mu. That means I'm going to be having mu here. That means this one is a and this one is a as well. This one is plus, I have plus, I have mu also, this one is for b and this also is for b. So this is what we have. So now in this case, this one is final velocity and this one is initial velocity. So I will decide to take initial velocity to bring it over because initial simply means where we start. So I will take initial velocity here. I will not transpose anything, the sign will not change because I will just take this here to start to write from this part to this part. Just the same thing. So in that regards, I will finally have m here. I will have mu a here plus mu b here. That's what I have equal to. I have also mv here a here plus mv b here also. So this is the equation we have for linear momentum. This one is very important in the study of what this area of momentum, right? And this is the equation we have. That means before collision, this one is before collision, before the bodies collide, the system of collision. This one is after collision, right? So now in this case, the next step is, since we have already have this particular equation, in this step now it will lead us to what we call something very important we call collision. Collision, earlier I defined this by saying is when two or more bodies forcefully come in contact. It's either they go with the same velocity or they go different velocity. If they move with the same velocity, that means that velocity we call it common velocity. Example, let's just say we have a car crash. That means there's a car coming there, another car coming there. If they collide together, that means maybe sometimes we are going to have a crash, or maybe the one car that is coming with a higher velocity, they are going to move towards the one that is coming with a lesser velocity. So this normally occur, right? And in the area of collision here is something practical that normally occur various in our locality, right? So collision here is the definition we have for it. Collision is going to be divided into two. Now it means I will have two types of collision, even though we have more than that. But I'm going to base on this particular two because they are much more, very more important in regards to collision. Now the first one I'm having here is going to be elastic here. That means we have elastic and we have inelastic collision. Now for the elastic here, I'm having elastic collision here. This one, I'm going to explain this in a brief form. And a collision is said to be elastic when it conserves both momentum and kinetic energy. Then when it comes to inelastic, it's said to be inelastic when it only conserves momentum and not kinetic energy. Right? This is the definition. Let me go over this because I'm going to give a mathematical expression, right, for it. Now for elastic collision, we are saying it's said to be elastic when it conserves both kinetic energy and linear momentum. When we come to this now, we are saying inelastic is said to be inelastic when it conserves only momentum but no kinetic energy, right? So the next thing is we are going to be looking at what we call the equation we have for this particular two, right?